Good afternoon, students. Now we are going to see a slab. There are two types of slab. One is one-way slab, another one is two-way slab. The slab spanning in a two opposite direction and also load carrying one direction is nothing but one-way slab. The one-way slab, the ratio of longer direction to the shorter direction is exceeds 2, that is called one-way slab. Next, two-way slab. So, what is meant by two-way slab? If the slab spanning in a 4 directions and also load carrying only both the directions, nothing but two-way slabs. If the ratio Ly by Lx is less than 2, then we call it as two-way slabs. Now, we are going to see a problem on one-way slab. I am taking a simply supported RCC slab for an office floor having a clear dimension of 4 meter by 10 meter with 230 mm wall all around, adapt M20 grade and Fe415 HYSD bars. So, that the data given in the problem is clear span is 4 meter, the wall thickness is 230 mm, live load for an office floor live load is 4 kilonewton per meter square, FCK equal to 20, there is M20 grade, we are for M20 grade FCK is 20, for Fe415 grade Fy equal to 415 Newton per mm square. First step we are going to see a thickness of slab. So, for a thickness we go for the span by depth ratio. If it is simply supported slab, the span by depth ratio is 25. So, that D equal to span by 25. We are taking 4 meter as span. I am putting 4000 mm divided by 25, it will be 160 mm. So, I just assume the cover D dash equal to 25 mm. So, therefore, total depth of the slab is 160 plus 25, 185 mm. Next, we go for a effective span. For effective span as per a IS 456 code, the clear span plus D and center to center of support, whichever is less, is nothing but effective span. So, clear span plus D, clear span is 4 meter, effective thickness span D is nothing but 160 mm, that is 0.16, so 4.16 mm. Center to center of the support, we are taking thickness is 230 mm, so we adding 230 mm, that is 0.23, then it is comes 4.23, whichever is less means 4.16 is less. So, therefore, effective span equal to 4.16 meter. Next step we are going for a loading. There are two kind of loading in the slabs, one is live load and other one is dead load. So, for a dead load we have to calculate the self height of the slab. If the depth of the slab is 185, the overall depth of the slab is 185, therefore, depth into unit weight of concrete is nothing but self height of the slab. So, here comes an 4.625 kilonewton per meter square. Next we go for a finishes. In this dead load finishes is coming. So, finishes we are taking as 1.5, it is assumed value. Next we go for a live load. For a live load, the problem already given in live load is 4. So, I am putting 4 kilonewton per meter square. So, overall total load is 10.125 kilonewton per meter square. For we are using limit state method. For a limit state method, the factor of safety is 1.5. Therefore, ultimate load we can calculate as 1.5 into 10.125, that is 15.11 kilonewton per meter square, the overall ultimate load coming for a slab. Next, we go for a calculation of bending moment and shear force. So, first we calculate the bending moment. For a simply supported beam, the bending moment value is W L square by 8. So, W is nothing but WU, L is nothing but effective span divided by 8. So, it is 32.86 kilonewton meter. Then we calculated shear force. Shear force value for a simply supported slab, shear force is nothing but WL by 2, that is the formula. So, in this formula W is nothing but WU 15.19, L is nothing but effective span divided by 2, it comes 31.60 kilonewton. Next step we go for a check for a moment of resistance. So, next step we are checking the limit of moment resistance. Moment of resistance is nothing but if it is mu is less than mu limit, the section is under reinforced. If mu is greater than mu limit, the section is over reinforced. We have to check the whether it is under reinforced or over reinforced. For that we have to calculate the mu limit. So, mu limit formula is 0.138 FCK BD square. So, we just substitute all the values, which comes 70.65, which is greater than mu already we are calculated in the moment of resistance, okay, bending moment. So, the section is mu is less than mu limit, the section is under reinforced section. Next, after that we are checking the under reinforced section. Next we go for a main reinforcement calculation. For the main reinforcement calculations, mu value is as per IS 456, the mu value is 0.87 FI AST D into 1 minus FI AST divided by FCK B D. So, in that all the values are known except AST. The mu value is already we calculated in the bending moment. So, we have to write it bending moment value 0.87, Fi is 415, AST unknown, D is nothing but effective depth. Next Fi is 415, AST unknown, FCK is 20, the B is nothing but 1 meter. For we have to design the design for a slab of 1 meter breadth. So, we can put it 1000 mm value. Next depth is nothing but 160. So, for that we have to calculate the AST. AST is 531 mm square. So, we are using the this is overall AST. Now, we are calculating the dia and spacing. So, for that we are if it is slab means we are going for a dia and spacing. So, using 10 mm dia bar for a slab, average diameter value is 10 to 12. So, I am using in this slab 10 mm dia. So, we have to calculate the spacing value is 1000 small AST divided by capital AST. Then we have to adopt the 10 mm dia at 140 mm center to center. Next, if you are calculating only main reinforcement, for a one way slab there is in shorter direction main reinforcement is coming, for a longer direction distribution reinforcement bars will coming. Okay. For a distribution reinforcement we have to provide minimum AST. What is the minimum AST value? 0.12% of BD as per IS 456. In that we have to calculate the 0.12 into 1000 into 185 divided by 100. The value is 220 mm. For that we have to provide the 8 mm dia at 230 mm center to center value. Next we go for a check for shear. Okay, we calculate all the reinforcement. Now we are going for a checking. There are two kind of checking in one way slab. One is shear, another one is deflection. First we go for a shear stress. So, for a shear stress we have to find out the nominal stress and permissible stress. If it is tau V is less than tau C, the shear is safe. If it is tau V is greater than tau C, we have to provide the shear reinforcement. Now, we have to check whether it is coming tau V is less than tau C or tau V is greater than tau C. So, first we have to go for a tau V. For a tau V, the formula is VU by BD. For a V is nothing but shear force, B nothing but 1000 mm, D is nothing but depth. So, tau V value is coming 0.198. Next we go for tau C. For as per IS 456 table number 19, we have to calculate the percentage of reinforcement. From the percentage of reinforcement, we have to calculate the tau C value. For the tau C value, we have to provide 0.29. Okay. For a solid slab, the permissible shear stress is nothing but K tau C. For K tau C, the K value as per IS 456, we have to according to the overall depth. We are in this slab, the overall depth is 185. According to that overall depth, we have to calculate the K value. In this problem, the K value is 1.23 and tau C value is 0.293. So, overall 0.36, which is greater than tau C. Therefore, tau V is less than tau C. The shear is safe. Okay. Next, we go for a deflection. Okay. So, what is the deflection? So, next step is, last step is in this problem is check for deflection. For a deflection, we have to calculate the L by D max and L by D actual. L by D is max is greater than L by D actual, then the deflection is okay. Now, let us see the L by D maximum. For L by D maximum, the value is L by D basic into KT into KC into KF. So, what is meant by KT? KT is nothing but if, as per IS 456 figure number 4, KT value is 1.5 according to percentage of reinforcement. For KC and KC is 1 value, because it is under reinforced. For a under reinforced section, KEC is 1. For a simply supported slab, the KF value is 1. So, altogether L by D maximum equal to L by D basic, that is for a simply supported beam, L by D basic is nothing but 20, and then KT value is 1.4, KC is 1, KF is 1. So, altogether 29. So, we calculated L by D maximum is 29. Now, we go for a L by D actual. So, L by D actual is nothing but the span by depth value. So, span by depth, we are now we are providing the effective span, that is 4.16 meter, that is 4160 mm divided by effective depth, that is 160 mm in this problem. Okay. The value is coming 26. So, therefore, L by D actual is 26, L by D maximum is 29. Therefore, the deflection is satisfied. Okay. So, now